All right, so let's get started. So we were in the middle of digital signatures the last time around. We'll take it out and continue. All right, so let's start from something that we left off the last time, which is collision resistant hashing. Right, so collision resistant hashing. Then we'll get back to signatures. Don't worry. Remind you, collision resistant hash functions, or we'll just call them CRH functions, are families of functions H, let's call it. It's a set of the collection of functions that map from n bits to, well, just put it this way, some L of n bits to n bits. Okay, so this is really a collection of collections, right? Each one is indexed by n, but Hn is itself a collection set of functions. Each function maps from L of n bits to n bits. What is L of n? Well, it had better be bigger than n because it's supposed to be compressive. Okay. There's some L bigger than n. Okay. So functions in this family are compressing, and therefore they have collisions. And therefore they have at least two inputs that are mapped to the same output. And the property of collision-resistant hash functions is that you can't find polynomial time algorithms. Of course, if you can run through the entire input space, of course you can find collisions, but you cannot do it in polynomial. Okay, so such that for every probabilistic polynomial time adversary A or collision finder A, the probability that A given H, where H is drawn at random in the family Hn. So this is all the statements I'm going to make are for large enough n. Right? So this is implicit in the description. The probability that A outputs a collision, which is x and y, both L of n bit strings, such that x is different from y and h of x equals h of y, this probability should be negligible in n. This is clear. Right? So this is the goal, and we started sort of constructing collision resistant hashing from the discrete log assumption, and we got a little bit stuck. Okay, so let's get unstuck. So there is one thing that there's one sort of key parameter of collision resistant hash functions, which is what is L of n. Right, so last time around we defined it as mapping from strings to n-bit, arbitrary strings to n-bit strings. I'm going to modify the definition a little bit, so now I want to map from L of n-bit strings to n-bit strings. Right. So what is L of n is really the question. Is it like 1 bit more than n? Is it twice as long as n? Is it polynomially longer than n? It's the parameter of the family. Okay, so here is a construction. So good. So here's a construction that we said. So H is parameterized by, well, each H will map Z P minus 1. So pick a group. Prime P, like that, let's say. H sub, okay, so each hash function will map from Zp minus 1 squared to Zp star, and the hash function will be parameterized by P, of course, and two generators, G1 and G2. And the function says H sub P G1 G2 takes as input x1, x2, outputs G1 to the x1, G2 to the x2, this is what we said. Okay, so first thing to verify, first of all, you can compute this in polynomial time, right? Compute it in polynomial time. Compress this. It takes two elements from ZP minus 1, which is what? Roughly log p bits, a bit less than log p bits, and compresses it into log p bits. So essentially 2 log p to log p is what it does. Now the question is collision resistance. Good. So we claim that this function is collision resistant. We have to be very careful. Turns out that it isn't. You have to modify things a little. Okay. So let me make things even more concrete. Okay. So let's say this prime p is of the form 2 times another prime plus 1. So p and p1. So, right, so these are safe primes, sufficient. Okay, so why am I doing it? Just to be concrete. Okay, so you have to pick these hash functions also efficiently, which means I have to pick generators, not just sample generators of ZP star. How do I do it? Well, I sample random numbers and check whether they are generators. Checking whether whether a number is a generator or not in ZP star requires the factorization of p minus 1. This tells you know the factorization of p minus 1. That's how you generate it. So that makes it easier, it makes it more concrete. Now the question is it collision resistant? Right? Let's try. Suppose, again, an adversary that gets a description of the function, namely g1 and g2, and manages to find a collision. Okay. Suppose, proof. Suppose A adversary given g1, given p, g1 and g2 outputs what? x1, we call it x2. This is an input to the function, and another input to the function, x1 prime, x2 prime, such that these two inputs collide. Such that these guys are different, the pair x1, x2 is different from the pair x1 prime, x2 prime, and yet g1 to the x1, g2 to the x2 equals g1 to the x1 prime, g2 to the x2 prime. Okay. I claim that this adversary, I can squeeze the discrete log, something to the base something out of it, right? Of some what to the base what? G2 to the base g1. Makes sense. So say g2 is g1 to the power alpha, some alpha I don't know. And in fact, since g1 and g2, since g1 is a generator, any g2 can be written as g1 to the power. Okay. Just that I don't know what alpha is, I'm trying to extract. So what does this mean? Well, you get g1 to the x1, g2 is g1 to the alpha, so g1 to the alpha x2 equals g1 to the x1 prime, g1 to the alpha x2 prime. Yes, I wrote everything in terms of g. And since g1 is a generator, this means that the exponents x1 plus alpha x2 equals x1 prime plus alpha x2 prime mod what? The group of the additive group of the exponent, which is p minus 1. Right. When I multiply things in ZP star is a multiplicative group. When I multiply things, the exponents add up. They add up mod what? P minus 1, because g to the power p minus 1 is 1. So, the guy's going to wrap around mod p minus 1. Yeah? This is what you get. Now you say, thank you very much. This is what, you have said. Alpha now is x1 minus x1 prime, right? Divided by x2 prime minus x1, or rather, times x2 prime minus x1 inverse mod p minus 1. And so this is what we said. X1 prime. So, yeah. So just linear equation in one unknown alpha, rewrite. Now, who was it? You. Raised an objection, very valid objection, that I can't always solve linear equations. Naturally, right? I mean, what if x2 prime minus x2, the inverse doesn't exist? Fair enough. Fair enough. Okay. Fair enough. So one utility of proofs is proofs, mathematical proofs. Another utility is actually to find attacks. Okay. So the fact that this proof doesn't work can be turned into an attack against this thing. Okay. What is the attack? Well, I'll let you think about it for a moment. Okay. But meanwhile, let's fix it. Now one way, but two ways. Okay. Yeah. So let me put it up for those of you who you know what, let me not parallel process. I'll give you a little bit of time to think about the attack. This is the second time in 68575 that I'm going through these motions. So it says, you know, it's a memory-less device. That, right, so you can find collisions. The collisions have to use, look, you know, if x2 prime minus x2 were invertible mod p, you're done. You're done. There's no gap in the proof. The only gap in the proof is that, yeah. So you have to use the gap in the proof to find collisions. Okay, let me give it a shot. Okay, you guys, you want to try? Yes.
Maybe because, like, if say given like
Yeah. Okay.
and then you know like a argument b mod 4, say, then if b is given, then you can just divide a over 2 argument b over 2 mod 2, right? The mod also reduced.
True, but you're telling me a way to solve this equation, yes? So one way to, okay, you know what? So the first thought is to say, look, you know, this doesn't work, yeah? But all I need is to solve the following linear equation. x2 minus x2 prime minus x2 equals x1 minus x1 prime mod p minus 1. Yeah? That's all I need to solve. Yeah, I mean, that's all I need to solve. We know how to solve these linear equations, even if, you know, stuff doesn't, you know, x2 prime minus x2 is inverted, yeah? Divide everything by the GCD of p minus 1 and x2 prime minus x2. Right? So divide it, this is the generalization of your example. Once you do this, yeah, so this you can do, right? Take the GCD of x2 prime minus x2 and p minus 1 and divide the whole equation by it. Okay. So now you get a number here. This guy also divides by GCD. Why can you divide by GCD? Because both x2 prime minus x2 and p minus 1 are divisible by GCD, this GCD number. So you can also, that guy also divides x1 minus x. So you can divide the whole equation by this GCD. And now it becomes an equation mod not p minus 1, but p minus 1 divided by the GCD of something. Right? Yeah. Now by definition, whatever remains on the left, x2 prime minus x2 divided by the GCD is relatively prime to p minus 1 divided by the GCD by definition. Now we can solve. And you get a solution mod not p minus 1, but rather modulo a smaller prime. Right? How do you lift it up? You say, well, you know, any solution to this equation has to be this number that I just found out, modulo p minus 1 over GCD. So any number that is whatever I found plus a multiple of p minus 1 over the GCD is a possible solution. So there are many possible solutions to this equation potentially, right? So you can do all these things. You can, but there could be an enormous number of possible solutions, depending on what p minus 1 over GCD is, right? In fact, fact, the GCD of these things could actually be a very large factor of p minus 1, right? Which means that you only get a solution mod 2. Okay? And then, yeah, everything is a possible discrete log. Half of the numbers are possible discrete logs. That didn't give you any information. You know, that made your life, you know, that made your exhaustive search faster than by a factor of 2. But thank you very much. You know, that's not very useful, is it? So it doesn't break discrete log. Yes, this reduction does not work in breaking discrete log. In fact, worse, there is actually, you can turn this into a, okay? So here's a collision. Let me just put it out there. Okay? So x1, pick x1 and x2 the way you want. x1 prime is x1 plus q. Okay, q is that q. Okay, p minus 1 over 2. That's q. And x2 prime is x2 plus q. Okay. I claim that this is a collision. Why? Why? Because g1 to the x1 prime, g2 to the x2 prime, yes, it's g1 to the x1 plus q times g2 to the x2 plus q, yes. This is g1 to the x1, g2 to the x2, times g1 to the q, which is what? I know that g1 to the 2q is g1 to the p minus 1, which is 1. And since g is a generator, this guy is a square root of 1, the non-trivial square root of 1. So therefore it's a g1 to the q, which is minus 1, times g2 to the q, which also is minus 1. And guess what? Minus 1 to the minus 1 times minus 1 is 1. So this whole thing is g1 to the x1, g2 to the x2, and voila, you have a collision. Okay. So I have to be a little bit more careful. Yes. Minutes? Now I gotta fix it. Yes, otherwise it's not fun anymore. How do you fix it, potentially? You can go back to the root of the problem, right? And then you say, you eliminate the problem. What was the root of the problem? The root of the problem is that the exponent group was, it's mod and composite number, right? That's where things broke. Okay? You could try to fix it. Okay. So this big cross doesn't work. Let me fix it. Okay. This time I'm not going to be lazy. Let me rewrite everything with making tiny changes. You are going to take prime. Okay, that's one. And the hash function maps. Okay, so instead of taking inputs from ZP minus 1, that's sort of what led us into trouble. I am going to take inputs from ZQ. Right? So in other words, I am going to work over a subgroup of ZP minus 1 with prime order. Okay. And then that every linear equation is solved. Has a unique solution. So G, let G be a subgroup of ZP star of order AQ. If you think of what is the subgroup has a good name. I mean, it has good properties. This is something that we are familiar with. Yeah. Turns out that this is the subgroup of, there's only one subgroup of order Q, and that is the group of quadratic residues. Okay. We know that quadratic residues MAP, there are half of them. Okay, P minus 1. So it is a group. There's a group of order P minus 1 over 2, which is Q, and this is that group. Okay. My hash function maps from ZQ squared to the group. Yeah, and what does it do? Well, that's what it does. You know, P, G1 and G2. G1 and G2 are random elements from G1 and G2 are random elements from G. The nice thing about groups of prime order is that every element is identical. Right? So, yeah, okay, they just pick two random elements. Of x1, x2 is G1 to the x1, G2 to the x2, mod. The exact same construction. All I changed was where the numbers came from, what the domain was. Again, let's go through the exercise again. Is it compressing? Well, it's not clear. I actually made the domain smaller, right? But not that much smaller, by a factor of 2. In other words, I lost 1 bit. Okay. So what is the domain size now? So this maps from 2 times log q. Yeah, that's the how many elements there? Log q. 2. I don't know. I'm going to write the output as an element in ZP star. So let's just say log p. Okay. The range is sparse, but I don't know how to further compress it. And my output is going to be the element of ZP star written in binary. Okay, so that's log p. Log q is what? It's q is what? Q is p over 2. So log q is log p minus 1. Yes. So I lost 1 bit. So this is roughly log p minus 1 minus 1, roughly log p minus 1. Still, I'm mapping something that is very close to 2 log p minus 2 bits or something to log p. I'm still compressing by roughly a factor of 2. So I haven't lost, yeah? Nearly at all. Right? So now let's run the proof. Okay, now let's go through the proof. Okay, now there's no quotes. The proof is, much of it is precisely the same as what we did, right? I get x1, x2, and x1 prime, x2 prime. They are a collision, right? And now my equation is of the form equals x1 minus x1 prime mod q. Why mod q? Because I'm working over a group of 4. And now you go. Now everything, well, careful. Okay. Now I still want to do it this way, right? x2 prime minus x2 inverse mod q. Yeah, this is what I want to do, and then I'm done. So at this point, I declare victory. I get the discrete log. Remember, alpha was a discrete log of g2 to the base g1. You're good. Yeah, this is if I can invert x2 prime minus x2 mod q. Can I do that always? Can I always do that? That's the question. Yes, no, yes.
I think so, is Q's prime.
Q's prime, and x2 prime is different from x2. Yes. So if x2 prime is different from x2, you're done. But what if x2 prime is equal to x2? Well, you know, is there another attack? See, you have to close all holes. But if x2 prime is, x2 prime different from x2, you're done. If x2 prime equals x2, what happens in this construction? You get, it had better be that g1 to the x1 equals g1 to the x1 prime, because the x2 cancels out. But that means that x1 equals x1 prime. That's because both are less than the order of the group. Okay, so this is if x2 is different from x2 prime, mod q. If x2 equals x2 prime mod q, then x1 equals x1 prime mod q implies that this is not a collision. Not a collision. Well, implies that x1, x2 equals x1 prime, x2 prime. So this is a trivial collision. Yeah, didn't keep it. implies a reduced trivial collision. Okay, it's one way to fix it. Yes.
So H is basically not mapping from ZP squared to G, right? It should map to ZP.
Say it again.
H should map to ZP, right?
H maps from.
It should map to ZP instead of G, right?
Let me just put it that way, okay? Let me write it this way. The point is that any element in the range of this mapping, any element that gets mapped to, lives in G. Yeah? Because G1 and G2 live in G, and anything you do with G1 and G2, they live in G. But never mind, because I'm not going to use this fact when I write down hash effects. I'm just going to write it down as a bit string, as an element of ZP star, as a number. Yeah? So, good, very good. Very good. Okay, so this is one way to fix it. Here's a second way to fix it, which you say, what? Well, I mean, if you have one solution, aren't you happy? Why second solution? Because this solution, I assumed that P is, in fact, of this very nice form. If it is not, then I need to do more. I need to pick elements from the smallest subgroup, smallest prime-ordered subgroup of, So I suddenly assume that P is of this form. What if I don't want to? Here is another construction. Okay, same thing. Let me write it down side by side. So here again, so this was so here again, G1, G2 are generators of ZP star. Okay, so I'm going back to the construction that didn't work, and I'm going to fix it in a different way. What does hash do? Hash takes x1 and a bit p. Okay, I'm not going to take big x1 and big x2. I'm going to do g1 to the x1 and g2 to the b. Yeah. Does it compress? You can again check. The input is like log p bits, or rather log p minus 1 bits, which is more or less log p, plus 1 bit, and it maps to log p bits. So that's compressed. You can check that the left is smaller than the right. The only thing I changed compared to that thing that didn't work is I reduced the domain, one of the domains, to be tiny, tiny. Okay, so very small, 1 bit. Now does it work? Well, the proof precisely the same thing. Okay, you go through the whole the whole motion, and what you get is again this equation of the form this equals x2 prime minus x2, but I called x2 b. Why? Doesn't matter. It's a bit. Okay, so this is b prime minus b. Maybe the other way around. I want to get, where did x2 prime minus x2 go? Okay. B prime minus b equals x1 minus x1 prime mod b minus 1. Okay. This, I claim, does the job for me. Why? Because there are two cases. Either b is equal to b prime, right? In which case x1 equals x1 prime, and the adversary did not produce a collision at all. The same story. The same reasoning that we used for x2 equals x2 prime. Or b is different from b prime, in which case what can b prime minus b be? It's either 0, it's either 1 or minus 1, right? We know that they are different. And 1 and minus 1 are both invertible mod p minus 1, regardless of what p minus 1 is. We found out. Okay? There you go. So b prime minus b is plus minus 1, always invertible mod whatever you want, really. And then you, okay? So, yeah, one way to fix it. But two ways to fix it. Here, I assumed something about the prime. I got factor 2 compression. Here, I did not assume anything about the prime, but I got sort of a 1-bit compression. Okay, so n plus 1 bits to n bits. That's the Okay, good. Yeah. It pays to be extremely careful in this business. All right, so, okay, so eventually what I need is a hash function that compresses by a factor of 2, by a factor of 3, some polynomial factor, okay? Neither of these constructions give me that. I mean, this guy compresses by a factor of 2, and this guy compresses by additive 1 bit. But I want to compress long strings to short strings. How do I do it? You know, I mean, either you could sort of extend this construction to compress by a lot, and that you will do in the problem set. So do algebra and extend this, or do something generic. Okay, so give me any hash function. So show a theorem of the form. Give me any hash function that compresses by, 1 bit. I'll give you a hash function that compresses by any number of bits. That's the kind of theorem one could hope to show, and we'll show exactly that. Okay, and then you're good. You can take either of these two constructions, put it through this compiler, and you get hash functions that compress arbitrarily. So this is what we're going to show. Then we'll move to signatures right away. So this is called the Merkle-Damgard construction. Basically, it's also called domain extension, because you have a hash function that maps from n plus 1 bits to n bits, and you want to map from n squared bits to n bits, but you extend the domain. Okay, so how does the construction go? Yeah, it's worth kind of thinking about things that, well, actually, you know what, let me ask you how you would do it without Googling for it. Yes?
Sorry, I have a question.
Yes.
How did we pick B in the second?
Be good. I didn't say it explicitly, so I didn't say what the domain is, right? So the hash function h maps from z3 minus 1, the same as there, times 0, 1 to zp star. In other words, b is either a 0 or 1. Right? So you look at your input, you split it, like take 1 bit out, the rest of it, interpret it as an element of p minus 1. Okay, good. All right, so let's try to extend. So here is a candidate. Okay, so my hash function now gets a very long input. Hash each of them separately, and add them up. So that is hash of x1 concatenated with x2 up to xl. L is very large. This is the sum of hash of xi. Okay, so you hash each piece, then you put them together. Why? Because why am I doing this? I could have done this too, right? Here is the candidate construction. This is hash of x1 concatenated with hash of x2, etc., 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 right? But that won't compress by very much. So that's why I don't like this one. I really want to compress to n bits. As many bits as before, as many bits as the output length of h, right? That's what I want. This is a candidate construction. So this absolutely does not work. Give me a collision. Yes. You want to swap x1 and x2, right? x1, x2, x0. x2, x1, the same thing. So you have So you have to do something, because you clearly have to do something more, right? There's several other things you can try, but I'm not going to go through all of them. Let me just tell you the constructions. Okay, I'll call this the line construction. So you have a hash, right? you're going to take a long input. You're going to think about it as, so your input is M, which is split up as M0, M1, up to M sub L. But think of M0 as long. It really doesn't matter, actually, to tell you the truth. Think of each of them as a bit. So basically take your message, split it up into bits. Okay. First thing you do. The second thing you do is the following. Okay. So your hash function takes M0 and M1, hash the first two bits. Okay. You produce something. You're not doing very much, right? Because you're actually expanding. You take 2 bits and producing ZT star in our construction. Okay. Hold on for a second. You take the output of the hash, you feed it in. So these are the inputs to the hash function. This is the output. You feed it in to the next iteration of the hash function, where the additional input is M2. Okay. So imagine that you have a hash function that takes, n plus 1 bits and maps it to n bits. Okay, so you should think about this as n bits. This is 1 bit, and the output is n bits. This is another 1 bit. The output is n bits. Keep going this way, and what you get at the end, you output. That's what you do. Now, why in the world did I do this, and why in the world would this possibly work? Okay. Why? Well, let's imagine that there is an adversary that finds a collision. So in other words, it produces M0 up to ML and M0 prime, M1 prime up to ML prime that collide. So let me look from the end to the beginning. What happens? Let me run both the inputs through the chain, right? Yeah. So I have ML, something that comes out. And then I have the other chain, which is this is the M chain, M prime, that's M0 prime, M1 prime, etc., etc. And now prime, then you get the output prime, and these guys happen to be equal. You produce a hash, you produce a collision. Okay, so yes.
Just to clarify, you take the first n bits as your M0, and then the next M1, etc. are which bits?
No, you can. Okay, so you can either do that, or I can just sort of make the construction uniform by saying M0 is everything is a bit, right? And well, the n bits that I feed here is essentially the bit followed by all zeros. You can pad everything to n bits. So this is nicer to kind of think about. It says, well, all these MIs are the same length. It's not like the first guy's n bits and then, that this construction doesn't do anything for the first few steps, right? Because taking 1 bit, the content of this message is 1 bit, and this is 1 bit, and then producing n bits. And like, well, I mean, it's not compressing, is it? But once you keep going enough, you will start seeing conversion. So you can do either one. Let's just think about it as everything is a bit. And first bit, I'm going to just pad it to the right answer, to a number 0 to the end. Okay, so this is okay, good. So you got 2 messages that collide. Okay, namely the output is equal to output prime. Okay. Now you start thinking about it. Say, well, there has to be a collision somewhere, right? Yeah. What does that mean? You look at ML together with what this guy is. Okay? So this is, well, you want to give it a name. So I call it x1, call it x2, up to xl. Okay, so this is xl minus 1. Okay? So the question is ML, is xl minus 1 concatenated with ML? Is it the same as xl minus 1 prime concatenated with ML prime? That's a question I ask. Either they are the same or they are different. If they are different, I found a collision. The last guy is a collision. If they are the same, if they're not the same, I found a collision. If they are the same, move one step behind, namely xl minus 1 is the same as xl minus 1 prime, which means I look at the previous one. Is xl minus 2 concatenated with ml minus 1 the same as xl minus 2 prime concatenated with ml minus 1 prime? Either they are the same or they're different. Okay, same story. Keep going. And then at the end, what happens is that you find that either you find a collision or the inputs are the same. By the way, the reason you reached at this point is because all these sort of primes were the same as the as the non-primes, which means that either the inputs are the same in its entirety, or you find a collision in one of the links along the chain. There. Right. So this is how you do domain extension. Good. Again, you have to be careful. So this construction, I'm not going to spring a surprise on you. This construction works. You have to be very, very careful. I could try to use this construction not just to hash L bits to N bits, like for some fixed L. I could also try to use it with variable length messages. Why not? I mean, what's stopping? I mean, I can keep hashing in my merry way, right, for longer and longer and longer inputs, right, potentially. Then you run into trouble. If the messages have variable lengths, different lengths, then I claim that this proof, whatever I just said, does not go through. And in fact, the same way that happened before, you can turn it into an attack. Okay, I'll leave this one, I'll leave this to your merriment. It's a puzzle. Is it problem clear? Person clear? This is a construction that maps long messages to short messages. It has to be long messages of the same length. Messages of the same length to short messages. If you don't do this, then you can find the lengths. Good. This is an exercise. All right. So now we have hash functions that map long to short. Now we're very happy. Okay. Now we can move back to actually our main business, which is constructing digital signatures. Okay, so does so we already did quite a bit on constructing digital signatures, so let me recap what we did. The first step was constructing signatures, one-time signature scheme, which means what? It means that the adversary can get a signature on one message of his choice, and he won't be able to produce a signature on any different message. Okay, that's what a one-time signature means. Okay? We constructed this thing, assuming just boundary functions. Assuming boundary functions, we call this Lamport construction. And what was the construction? Just remind ourselves. Can anyone tell me, by the way? phenomenal memory, plus to plus. Can you remind me what it is? I have to come up with verification keys and signing keys, secret keys or signing keys. Right? So, and signing keys. And I'm going to sign, let's say, fixed length messages, n-bit messages. So, sign n-bit messages. And one of them. This is what I wanted. Good. So, anyone remind me? Yes.
You have like 2n bits, like x0.
2n pairs, actually. So now it's quite important that, so my signing key is 2n pairs of numbers, 2n numbers. And I'll call them x10, x11, x20, x21. Write them nicely in this array, right? xn0, xn1. And each xij is a large number. It's not a bit. Is a large number. It's is a number from 0, 1 to the k. K is a security parameter, let's say. And now I'm going to also assume that there is a one-way function f that goes from 0, 1 to the k to 0, 1 to the k prime. I don't particularly care that k and k prime are the same, just some k prime. And given this, the verification key is f of x10, f of x11, etc., etc., f of xn0, f of x. Just apply f to each of these numbers, to a number separately. Okay. So what is the signature? What is the signature? Signature is just, well, pick out a subset of these 2n guys, n out of 2n guys, and which n? Well, the ones labeled by the bits of the message. So in other words, x1 and 1, x2 and 2, etc., 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 xn and 1. This is the signature. How do you verify? You take this guy and say, well, you have a message and you get a signature, right? And you want to check that things work out. How do you do it? So you apply the one-way function f in the forward direction to each of these guys and check that this is equal to the right one of these guys. Okay. You know which one it should equal because you know the message, you know the first bit of the message. Okay. So verification. So let me give these names. Okay, so we'll call this y10, y11, yn1, and yn0. So you check, the verification algorithm checks that for all I, f of signature, let me also give these names, sigma 1, sigma 2, up to sigma n. Check that f of sigma I equals y sub I comma mi. It's a formal way of writing down what I just said. Signatures and numbers. Apply the one-way function to each of these numbers and check that when you do it, you get the right one of these two. That's what. Okay, so that was the first step. The second step was, well, we said, so this only signs n bits. Actually, even worse, right? I mean, I could, what is n? I mean, n is up to my choice, right? I could, n is 1,000, n is 10,000. I don't care, right? I can make n as much as I want. The real problem is that the size of the verification key and the size of the signing key grow with it. Okay. Another way to put it is that, when I set up my signature system, what do? Right when I publish my verification key, I'm Amazon, I publish my verification key, keep the secret key to myself, and later I say, well, I'm going to sign stuff. The point is that once I publish the verification key, I commit to how many bits I can sign with this key. Yeah, I pick n, I publish these many guys, I can sign n bits. N plus 1 bit, tough luck. Okay, so that's the problem. The question is, can I make this guy sign many bits, arbitrarily long? It's still a one-time signature, but long message. One-time signature signs long messages. Long meaning poly n length. Poly n bit messages. And this I will assume one-way functions plus collision-resistant hash functions. So really, in the content of what I'm going to do here is not so much that you can sign poly n bit messages. I mean, that's useful too, right? But the point, the way I'm going to use this is that the verification key in the first Lamport scheme, the verification key was at least as long as the messages I could sign, right? Concretely, yeah, that's a problem. In the new scheme, the verification key is going to be shorter than the messages I can possibly sign. That's a concrete benefit that I will use. Okay, so how do you do it? I'm not going to write it down again. We sort of described it the last time. Instead of signing the message with this Lamport scheme, first hash the message using a hash function, right? And then sign the hashed message. That's what we do. Where does this hash function live? I mean, someone has to pick the hash function, right? The signer cannot, I mean, the person who is trying to sign cannot pick the hash function because the signer could be malicious and he could say, well, I'll pick the hash function so I can find collisions. Doesn't make any sense. The hash function has to be picked by the person who set up the system, the verification key and the secret key. And the hash function has to live in the verification key. Okay, so the way it works is you do exactly Lamport, set up the secret key verification key, you pick a hash function, and you put the hash function in the verification key as well. Okay? Now, when I sign, I hash the message, and then I sign using Lamport to check, to verify. Well, again, hash function is public. Anyone can hash and then verify using Lamport. Right? So I'm not going to write it down, but we did it the last class. Okay, so quick reminder. Okay, so what we're going to do now is to say, well, I'm not happy with the one-time signature scheme. I want to really get a signature scheme where you can get signatures of message 1, message 2, message 3, polynomially many. Still, you won't be able to forge a signature for a new message. That's what I want. Right? That's what I want. That's what I want. So let's try to do it. Rather, a terrible looking idea, but not so bad. Here's what I'm going to do. So look, I mean, I set up a verification key, right? I'm assigning a key for myself. I get a new message, right? I get a message. I can either run Lamport or Lamport plus hash or whatever to sign this entire message. But the problem is that I lose the verification. I can't use the verification key anymore. I lost it. I mean, if I use it one more time, we saw with Lamport that you're dead. Lamport is not a two-time signature scheme. Very not a two-time signature scheme. Okay. So again, remember the Stanford experiment? Either you have marshmallows, right, and I can sort of be greedy and go eat them all up, or I can be careful and wait and use them more prudently. Now, context. Here's what happens. Don't use the verification key to sign. Don't use up the verification key to sign a message, but rather do the following. Okay? Do the following. You have verification key, your verification key is VK. Let me call that VK0. Why 0? Because it'll be a 1. This is your original verification key. You get a message, right? Many bits. You're going to sign a message 1 bit at a time. Okay? You're going to sign 1 bit of the message with VK0. But while you're doing it, you're also going to generate a new verification key signing key pair. Okay? And you're going to sign not only the 1 bit of the first bit of the message, you're going to sign the first bit of the message concatenated with the new verification key. In other words, you're saying, look, I generated this new verification key, it's not in the PKI, I just generated it. And I'm going to authenticate it using my real verification. Okay, so let me just write it down. Again, so I'm going to call it sign prime, okay, of M1, M2 up to ML, let's say. It's going to do the following, sign using the secret key. I'm going to generate a new secret key verification key pair, SK1, VK1, let's say, comma SK2, VK2, etc., up to SK VK. Yes? As many as the length of the message. So now I'm going to do the following. I'm going to produce sigma 1, which is a signature under SK of the message M1, first bit of the message M1 concatenated with VK1. So I'm going to do. Sigma 2 is a signature under not SK. I mean, that's the thing, right? I mean, I can't use SK twice. I'll be dead immediately. Instead, I use SK1, because that's what I just generated. Of M2 concatenated with VK2. So every time I'm signing one bit of the message, and I'm generating new things that I can use to sign the next bit of the message. Keep going. Right? And so on and so forth. And from sigma L, sign SKL minus 1 of ML concatenated with VK2. Yes, this is the signature. Signature is about not the secret keys, but all these verification keys and all these sigmas. They together form a signature of the message. Right? How do you check? How do you verify the signature? Well, you verify the entire chain, right? You get a message, you get the sigmas, and you get the VKs. Say, well, is sigma 1 correct with respect to the message 1 and verification 2? Is sigma 2 correct with respect to message 2 and verification 2? Keep going. Right? This is called a signature chain. Yeah? What you do. And now the question is, what happens when you, so this is, I got a message, okay? So I signed it. I get another message. What do? I only have two choices. Slightly. Yeah. Get another message. What do? I could repeat the whole process again. I could say, look, that's it. Start from scratch. Generate SK1, VK1, blah, blah, blah. Yes? New SK1, VK1, new SK2, VK2. Question is, this is a good idea. Remember, these SKs are objects that if you touch them twice, you're dead. There's no security anymore. That's it. Okay? So, you give me this message. Well, I'm supposed to sign it for you, right? You're the adversary. You give me another message. Well, I'm also supposed to sign it for you. Keep going many, many times. I'm supposed to oblige you. The second time you ask a different message, suppose I redid this whole process. In other words, did everything again. What happens?
You leak SK.
Why?
Because they can do the same thing, like just sort of peeling back all the way through to. Well, you generally.
Say again? Yeah.
If you have them sign all zeros and all ones, then you leak SK.
Good. But okay, so good. So you're going sort of one level deeper than this is the assembly language attack. The sort of the C attack is to say, look, if I do this again, I am going to produce a signature of the first message together with the first verification key that I generated. Yes, that's the first part of the signature chain. The next time you give me a message, I'm going to give you sigma 1 prime, which is signed with what SK? The same SK. I mean, I have to start from somewhere, right? Same point. Of M1 prime together with BK1 prime, whatever that means. Now I'm dead because I used the SK twice. Dead. Okay? That's not going to work. This is still a one-time signature scheme if I use it this way. Okay? The right way to use it is the following. This is terrible. The right way to do it is to say store SKL. In other words, so this is a chain, yes? So you start from 0, SK, SK1, SK2, etc., etc., etc. The next chain, what I did there, which didn't work, was I started from the same point. Yeah? And when I have out degree 2, I'm dead. That's a way of looking at it. Okay? So the only way to solve it is to say, well, store SKL. The next time I get a message, start from SKL. That's the beginning of your chain. Keep going from there. Yeah? If you think about it, if I begin from here and start signing, so this is signature of M1, M2 up to ML. I start from here with SKL plus 1, L plus 2, and so on and so forth. And here I sign M1 prime, M2 prime, etc., right? To verify, the poor verifier, he needs to know the entire chain, right? Because he needs to start from the beginning. That's the root of trust. That's the only thing which is in the directory. Okay, it says Vinod has this verification key. Everything that happens in the middle is temporary. No one trusts what's temporary. So the poor guy has to start from the beginning, go through the entire signature chain for M1, and then start verifying the signature chain for M2. No, I'm Amazon. I keep signing stuff for you, right? The verification time for the teeth message is the length of the history, like how many things I signed in the past. Okay, that's not good. Right? That's not good. Right? So this works in the sense, well, I suppose you have to prove security. Okay, prove security. Which we will. These argue security. Yeah, okay, you know what? Let's argue security, okay? So, you ask me for a signature of a message, I give you the chain. You give me another message, well, remember, I remember the state from before. I extended the chain this way. Another message, well, further extended the chain. Keep going. So the whole thing is a big, huge chain. Now you tell me, you know what? Thank you very much. I've had enough signatures from you. I'm going to produce, you're the adversary, you say I'm going to produce a signature of a new message. Some other message. Now I say, I'm going to catch you. Why? So here is the entire signature chain that you got, right? So M1 of ML, M1 prime of ML prime, M1 double prime of you keep going, right? This is the entire signature chain you got. And now you have to produce a valid signature chain for a different message. So how do you do it? Well, you have to start from here. Every signature chain has to start from the verification key, my verification key, the one that is in the PKI. It has to start from the same root. Now you say, well, you know, I look at the signature chain you produced. You say, well, this is a valid signature chain. You look at the first signature and say, well, did you sign M1 together with VK1, the same VK1? Yes? Yes or no? If you sign something different, well, then you broke the signature, one-time security of the signature scheme, because I gave you one signature under SK, you produced another signature for a different message. So it has to be that the first element in your signature chain, the forgery that you produce, is the same. It signs the same message as before. What is the message? It's one bit of the real message together with the next verification key. So in other words, the next verification key is the same as in the original chain. Now I say, well, let me move on to the next one. Okay. Did you sign the same thing that I signed using VK1 or a different thing using VK1? Yes or no? No, you forged a signature with respect to VK1, right? I gave you one signature. Yes, move on. You get the point. This is how you argue security. One needs to really translate this into a proof. Okay, so the main thing that is not satisfactory about this thing, well, there are many things that are not satisfactory. One, I need to store, as a signer, I need to store the line, because every time I get a message, I need to start from the end of the line. Signer. The verifier needs to start from the beginning of the line and move through to verify any given message. Yes. So both the verifier and the signer are kind of in bad shape. Yes.
So your argument of security is that when you go through sort of like validating the chain up to the point of the last message that was sent, if they had changed any of the bits, then
So the game
what
is
about like the extension at the end, right? If they're signing a new message, aren't they going to extend the chain?
Good, but if they did extend, the argument carries over all the way to the end, right? So let's say for a moment that I gave you many messages, so a huge long chain, and now you gave me a signature of a new message that extends at the end.
Right.
What did you do? There is SKL, which is what you're supposed to use to sign, right? I never gave you a signature of anything under SKL.
Right.
And you just produced a signature of something else. So it's not even a one-time signature break, it's a zero-time signature break, right? And that's impossible. So breaks in the middle, if you try to branch off from the chain at any point in the middle, you break a one-time signature scheme, one-time security. If you branch off from the end, you break a zero-time security, which is an even harder thing for you to do. Zero-time security, breaking zero-time security is like, I give you the verification key, go, right?
Okay.
So either one, good question. Okay, so both the signer and the verifier are screwed here. But we are using a line. Yes. Have you, let me rewind your memory. Okay. Have you seen this before? This phenomenon happening before? Remember all the way to when we tried to build a symmetric key encryption, secret key encryption scheme from pseudo-random generators. Okay. So how do I encrypt a bit? Well, I run the pseudo-random generator. If you think of the pseudo-random generator as one of these like Blum-Micali, the one-way permutation techniques, computing the ith bit is you do something, then you do something. You apply F, you apply F, you apply F, you apply F many times. Then you get a bit, and then you XOR parity. So one-time parity with the message, and you go. So what is my running time for encrypting a message? Well, I really have to run things all the way through. And it's stateful on top of it, which is, you and I have to agree on where we stopped. So, and it happened, and then we solved it, right? I mean, because we didn't give up there and go home and say and cry. Okay, so we solved it. And how did we solve it? A tree. A tree is the answer to life's problems. Okay, so a tree helped us there. A tree must help us here. And indeed it does. Okay, so here is the way that happens. And that will give you a real signature scheme. Okay, so let's try. In fact, I wanted to do it in 2 steps. I'll still do it in 2 steps. So here is my here's my verification. Okay. So I'll call this VK bar. Why? Because I'm going to use another scheme with the little VK to construct this verification. Okay, so this is a new scheme. The real scheme has algorithms gen bar, sign bar, and verification bar, and keys pk bar and sk bar. Okay. And the old scheme has old meaning a one-time scheme has vk and sk and so on. All right. So here's what I'm going to do. I think it looks ridiculous, but now I'm going to have a tree of depth. How much? Well, the length of the messages you wanna assign, or really the output of the hash function. So n bits. So the depth here is n. Right? If you want to assign a message that's longer than n, just hash it down to n and sign it. That's the way. That's why I'm going to fix it at n. And I'm going to populate the nodes of this tree by verification keys and secret keys. Okay, really only verification keys. So I'll call this verification key epsilon. And this is verification key 0 and verification key 1. This is verification key 0, 0 and 0, 1. And verification key 1, 0, 1, 1. Keep going. Right? Really exponential, 2 to the n, roughly 2 to the n. Many verification keys. Okay, this is my verification. Now you might object and say this is way too long. Indeed, it is way too long, but hold that thought for a second. Okay, this is a verification key. Secret keys are, well, the secret keys are associated with secret keys. Okay. How do I sign a message? And message now is without loss of generality n bits, because if it's longer, hash it down. How do I do it? Again, remember GGM, it's not like well, it's a tree, so I suppose that's what it is. So what am I going to do? Let's say for a moment that writing it in generalities, so example, the message is 0, 0, 0. Okay. So I look at the message defines a path in the tree, right? So that's 0, 0, 0, 5. What I'm going to do is I'm going to produce a signature under. So vk epsilon, by the way, is the verification key, and this is my verification key, and that's what I'm going to, I guess, publish. This is the published verification, the root of the tree. The rest of it is in my mind. I'm going to keep the tree in my mind. So I'm going to sign under vk epsilon. Sign under sk epsilon as the key. The message, I'm not going to sign a message bit yet. Okay, so vk0 concatenated with vk1. Sign the children, the verification key of the children, using the secret key of the parent. Okay, don't stop there. Move down the chain, right? So this sign under sk0, which is basically sk0, vk, well, the two children, 0, 0, 1. Keep going to the right. So far I didn't sign the message. Yes, I just signed the verification keys, but I went along the path defined by the message. So that I did. I am using the message. Eventually, I get, there is a secret key here, there's a verification key here and the associated secret key, which is all zeros. I'm going to sign under secret key all zeros the message. That's it. Okay, so the message kind of hangs down from here. 0, 0, 0, 0, hands down. That's it. Okay. We're not done, but the good thing here already is that the running time of the verification algorithm, right? So this is what I do the first time around. The second message, well, I still start from the root, go down the message path, and I do the same thing. Yeah? I'm going to do precisely the same thing. Yeah? that was problematic for us with the line. I mean, if the first message started from the root, if the second message also started from the root, that was problematic. I said that. I don't want to do that. That's why I put things at the end of the chain. Here, it's not problematic. So that's the first thing to ask. Why is that not a problem here? So to do that, let's think about what happens with the signature of another message. Let's say 11111. Well, so what does that look? Well, that looks like the following. It looks like the signature of, under the same secret key, the root secret key, what? Its children, right? That's how I always start. So you say, look at it. I mean, you produced two signatures under the same secret key. You are dead. But no, because I signed the same message using the secret key. And if you look at Lamport, the signature is the same. I mean, if I sign the same message twice, you get the same signatures. Okay, so yeah. Not yet. Nothing really happened yet. The next time around, I'm going to deviate from the path, from the 0, 0, 0 path. I'm going to move along one path. So in other words, I'm going to sign with SK1, VK10, VK11. So now I am not, these secret keys, I'm not going to use them at all because the path for 0, 0, 0 and 1, 1, 1 do not intersect except in the beginning. In the beginning, it's the same message that I'm signing. And I say, oh, you know what? That's not so good. Maybe the second message is not 1, 1, 1, 1. Maybe it's 0, 0, 0, 0, 0. The last bit is different. Okay, good. Again, the same thing happens. This is the same. This guy is also, well, I have to use a 0 secret key. And I have to sign 0, 1 and 1, 1. But look, these guys are the same. Yes, I'm signing the same thing all the way until the very end when I'm using a different secret key to sign the message. So I'm never using the same key to sign two different messages. And that's why that's why it's not a problem to kind of go back and start. Okay? The good thing about it is that the verification algorithm is quick. How much work does it have to do? It needs to verify n signatures. Okay? N is good. Okay? Polynomial in n is good. Okay? Things that depend on the history of how many messages are signed, not so good. This is okay. All right, so the verifier is happy now. How about the signer? Not so much, right? Because he has to store this entire, tree in his head, and what's that about? You can sort of do one optimization right away. I don't have to generate the entire tree. I can generate it as and when I go. For instance, when I want to generate the 0, 0, 0, all I need to do is generate the verification keys along this path, and a bit more. What bit more? The siblings. The siblings along this path. That's all I need to generate. That's not too much. Right? And as and when I keep signing more and more, I keep adding to this more and more, but it's not exponential. Right? That you can already do. But even that doesn't make me happy. If I keep signing, I'm going to get a seg fault. Okay, so eventually I sign many messages, I'm going to run out of memory. That's not so good. Okay, so here's the way you fix it. You say, look, these verification keys, okay? How did you generate these verification keys in the first place? You generated the secret keys. Think about Lamport, right? You first generate the secret keys, then you applied a one-way function to them, and you generated the verification keys. So secret keys are random objects. I don't need to store all this randomness in the tree. I could set the secret key for any node to be the PRF of the node with some seed. And all I need to store is the seed of the PRF. Okay? I never need to, there's a compressed version of it. That makes my life as a signer easier as well. So my space requirement is now to store the seed. Now, if you say PRF, what PRF? What are you talking about? You know PRF, right? In fact, I only told you one PRF, which is the GGM, the tree PRF. So if you use that tree on top of this tree, what is it? Is it a tree or is it something else? Turns out that it is a tree. So this whole construction looks like the following. This is a GGM tree. Okay. This is the root. This is the seed. Yeah. At any point, it looks like a tree with flowers. Okay. So at any point, the seed gets expanded not 2 ways, but 3 ways. 2, as usual, you generate the left and the right child, but you also use a little bit more bits. You're going to expand n bits to, I don't know, 2n plus something bit. And those plus something bits you're going to use to generate a secret key verification key. Here, again, I'm going to expand 2 ways, okay, but with a flower. Okay? Verification key, SK0, PK0, so on and so forth. Okay. Now, this is what the construction looks. If you put everything together, this is what it looks like. Okay. I'm way out of time, so I'm going to stop. We'll still do signatures in the next class, but a different take on signatures. Thanks.